Analytics. Number. Okay, like we're going. Okay. Viewers, analytics. Seem to be going good there. Good there. So that move this one over here. Back to restream. Okay, hello. I'll be chatting to Twitch and YouTube, but LinkedIn will not get these chat message. That's okay. That not working. Yeah. Interesting. Not happy about the chat. Right. Interesting. Chat was working before. Okay, well, I will respond to chat the best we can. I don't think there's any way enable chat. Okay. I'll bring up the chat windows. We'll be starting in about 2 minutes. I'm just making sure all the streaming options are happy and ready to go. About chat. Hello, YouTube. Hello. Okay. Okay. Starting soon. Okay, so it's 10 o'clock. We're gonna go ahead and start the live stream. I am FPGA Zealot, or Andrew Wilson, and we'll be looking at Sundance's VCS3 3D kit. They provided this kit, and I'm doing a fun little series or campaign looking at the different options. There's not many FPGA development systems, platforms that you can do MIPI display or MIPI camera. So this is a very unique platform that you can do display and cameras on. So I'm really interested in exploring those applications with the AMD FPGA. So today we're going to bring up the FPGA board in Vivado, look at some of the basic settings, how we bring in the correct settings and set it up to do a basic hello world on the application processor, the real-time processor, and a soft processor, and look at some dry stone benchmarks. As I said earlier, I'm FPGA Zealot. We are streaming on YouTube, Twitch, and LinkedIn right now. You can find me on LinkedIn as Andrew Wilson. I also post on X for some fun FPGA updates. And some disclaimers. This is not a paid sponsored. I'm doing this more for just the fun and exploring the MIPI display and MIPI camera IP provided by AMD. I'm not employed by AMD or Sundance. I do not offer official support for these products, and the content on this channel is created for informational purposes only, and all opinions expressed in this channel are my own. So today, this kit I have on the left, we have a 3D printed case with a display, forward-facing camera, backward-facing camera, and a very tiny FPGA embedded system. I don't really want to call this a SOM. It doesn't really have a connection. This is more of a standalone, small, probably one of the smallest Zynq UltraScale Plus platforms available. You can see the picture on the right, kind of scale to a hand. If you have any questions or want to say anything in chat, I will try to respond to you. It will be a little crazy, but I have the chat messages open up here. Feel free to say hello, where you're from, your interest in the Sundance 3D kit, AMD MPSoC, FPGAs in general, video applications. Feel free to say hi, ask questions during the live stream, and we'll try to answer them as we go along. So let's look a little bit more into what this product is. The block diagram here, kind of the upper level PCB block diagram. We have the rectangular package for the AMD FPGA, our system on chip with the hardened processors. For memory, you have the boot ROM, which is a QSPI. We have, I guess, then we have the eMMC, which you can access mostly through Linux to have your Linux OS, which is great having a built-in eMMC like that. And then for operational, you have LPDDR4, 2 gigabytes. Very reasonable for how small this package is. Then we have 4 separate MIPI connections. Looks like 2 camera and 2 display for this platform. I think you can repurpose those between cameras and displays on the other platform or on the board itself. And then most of your data is going to be going through the USB-C. You're using the GT lane, so I think you can get up to 5 gigabits per second. I'll have to look at what the upper limit for the PS USB-C interface is, but you can do a lot of interesting things with that, which I want to explore in later streams. And then mostly it's just UART, CAN bus, and IMU, and JTAG. Those are the systems that we have available. Digging down a little bit more into the AMD MPSoC, we have the ZU3EG, we have quad-core application processors, the A53s, we have dual-core R5s, which can run in lockstep for additional reliability. There is a Mali core for, they call it a graphics processing unit. I still need to find a good example of it. I have yet to see like a good example of the Mali core that's easy to demonstrate and to play around with. So that is one of the things I do want to get running someday. But we may be moving on to newer platforms by the time I get a good example going. We have LPDDR4 for this example and the USB 3.0 off the processor. We also have 150K system logic cells, which is really reasonable for this package size and the platform that this is on. The block RAM, I don't think we have any URAM. I think it's all block RAM, 9.4 megabits. And then the DSP slices 360. This is very important for our camera and display video processing. And in future videos, we'll see how that utilization is important and how much you can use DSPs in the video processing. So Sundance is providing a voucher coupon. So Sundance is a UK-based company. I think their full name is Sundance Multiprocessor Technology Ltd. They do a lot of embedded computing solutions. Feel free to pause or whatnot to get the voucher. This is a 50% coupon for the systems that we talk about today. I'll come back to this in a minute. But Sundance, they offer embedded solutions with these standards, OpenVPX, PCIe. They also have modules, Groovy. If you're familiar with the Trend-Z company, that they have the Groovy standard, FMC modules, mini PCI modules. So they offer a lot of embedded solutions for mostly including FPGAs. I'll have to see if they have any CPUs or GPU solutions as well. And on their website, VCS3-3D-kit, you can find this product. This provides a whole 3D kit, I believe. But you can also find, I'll post the 3D printed CAD files on a Hexter.io article. But this provides all the hardware, I think, to get up, but you can also kind of buy it piecewise. You can buy the different boards and whatnot to do the project yourself if you want to do it more, if you want to do a different setup. But they do offer the different solutions. So this is the whole kit. This is what I'm working with today. You can also get the board by itself. And so far, it seems relatively easy to bring up. I do know that it was the power. Where's the power coming? Okay. Cables. But I think there's an example of how the system is powered here. Yeah, it looks like we're being powered over this cable right here. And that's the UART. Okay. And if you want more information on the AMD Zynq UltraScale Plus device, there's plenty of good examples and documentations on the AMD website for more details on the EG device. Once again, here's the voucher code. I'll show it a few times during the stream, but this is the voucher code that Sundance is offering. I mean, not the code, but email it. They'll get the code. They'll confirm that you participated in the registration of the event, and they'll provide you the discount for the products. Okay. We still have a good audience. Feel free to say hi or chat. But we're going to move on to actually building this project and looking at how we interact with the FPGA and how we can do a very basic design to demonstrate the tools and utilities that are available. So first, we want to get the board files. So Sundance Multiprocessor Technology has a VCS3 public repository. They have a board file section, so you can download the zip file or git clone it, wherever you feel you want to. But when we open Vivado, I'm going to use 2025.2, the newest version. We can reference that board file repository and begin a project, a new Vivado project with all the hardware information available. So if we go to Tools and Settings, So if we go down to Vivado stored board repository, you can just add the link to the Git repository subdirectory board files. Apply, hit OK, and now when we create a project, we'll be able to reference that board. We're just going to do a basic RTL project, don't specify any sources. We're going to go to the board section. Easiest thing is to just go to vendor, go down to Sundance, and we have the VCS3 ready to go, where it has the part already specified for you. And then we can begin doing a basic block diagram, get the processor set up, and add a soft processor as well. We have a question on YouTube. Hi from Florida. How do you plan on bringing up which Linux? So we're going to do bare metal example today. We're going to be looking at doing maybe Peta Linux and the new Linux EDF in a future stream. But there's a lot of bare metal. Using bare metal, you can do a lot of prototyping on this hardware, be able to explore the different interfaces, to interact with different soft IP in the FPGA. But we do want to look at Linux in the future streams as well. So we're going to create a top block diagram design. So to bring the processor in, we're going to do mpsoc. And we're going to run block automation. So this will take all the configurations that are in the board files and apply them to your design. And we can double click this to see the different settings that have been configured. There we go. So advanced view. So we can look at with the IO configuration, DDR configuration. So let's look at the IO low speed. Expand all of this. So we have our dual parallel QSPI. Okay, that's really good. That's a lot of QSPI memory, dual parallel. We have the eMMC, the CAN bus, I2C buses. I believe these are mostly for onboard components. And SPI buses, UARTs, GPIOs. And then we have the USB. We have the low speed connection, and then we have the high speed connection here. And I think we can go to clock configuration, the GT lane configuration. We got 26 megahertz reference clock. I'm not sure what the full speed on that's going to be. We can also look at the DDR configuration. We got LPDDR4, and we have 2 gigs. Any other useful information? We're not doing PCIe, we're doing isolation. So that's our basic system. To get a complete diagram, we're just going to connect the clocks up, and then we can be able to export this to Vitus. We're just going to export the hard processors right now to Vitus, and while Vitus is building, we can come back and add a soft processor. So we validate it, we save it. We're going to go to design sources. We're going to create an HDL wrapper. We're doing the default settings. Let's Vivado handle any changes. So next, we are going to go to export hardware. Okay, wants us to generate. So we're going to start the generation process. And then once most of the IP threads, our out context builds have been set up, we can export the design and get Vitus going. Okay. Okay, now we're in this state. We can put this in the background, and we can go ahead and start the export process. All right. Good. So I guess we'll have to wait for this to finish. Take too long. Any other questions to fill the quiet void? Okay. Go. Export hardware. We're just doing the pre-synthesis, so no bit file, but it's just looking at the hard processor. Give it the default name. As soon as it's done exporting, we'll open up Vitis and get the platform up and going. So now we're going to go to Tools, Launch Vitis IDE. While this is building in the background. We're going to set a new workspace in our directory. And we're just going to call that workspace 0. And then we're going to do a new platform component. And we're going to go ahead and select the XSA file that we just exported. And we'll let it start creating the platform. We're going to go head back to the Vivado project and start working on the soft processor. As this gets going. Hey, Paul, you asked a question in LinkedIn. Yeah. So feel free to ask questions. I will try to read out the question. So Paul from LinkedIn asked, is there any chat in the presentation? I don't have any chat overlay right now. It can get in the way. So I will try to repeat your question. So feel free to ask questions in LinkedIn, YouTube, or Twitch, and I'll try to respond. Real quick. Okay, so we're going to do the standalone, let it generate, and it's going to be working on creating the platform in the background. And now I want to go here and add a soft processor. So we're going to go and do the MicroBlaze, and we're going to do the RISC-V version of the MicroBlaze, add that to our block diagram. We're going to run the block automation. We're going to want 64 kilobytes to run Drystone. I don't think the package, the BSP kind of requires that much space for the MicroBlaze. We're going to turn off cache. We're going to enable UARTs. We're going to interrupt controller. And we'll just do default preset. And we'll see what performance we get. So we have the RISC-V processor, and it's not really connected to the hard processor. It has its own standalone local memory, which we have set up as 64 kilobytes. Now we're going to add the timer. So this is important for the dry stone. So we're just going to hook up the timer, connect the interrupt to interrupt 0. We're going to add the debug interrupt to interrupt 1, and then we're going to connect the bus here. We're going to ignore the other one at the moment. Okay, we have a great question from James Bickerstaff. But we need to update the XSA upon adding it, the soft processor, and adding other IP, or does Vivado and Vitis handle that? Currently, you're going to have to manually export the XSA file. You can potentially use a script, a Tickle script, in your build process that properly exports it to where you expect it to be, and then you can run your Vitis, Petalinux, Linux EDF build script to pull in the new XSA, but there's no automation of XSA porting that I'm aware of between Vivado and Vitis. We're going to have to manually update the XSA in Vitis every time we bring in a new system. You can rewrite it, and Vitis will sometime recalculate it, but I have, at least in the old tool, that has not been a reliable process. Okay, so we're going to go ahead and validate the design. Brian Fletcher on LinkedIn in the comments section, he has added a link for asking questions for the Zynq UltraScale Plus and the AMD Vivado Vitis tool. So feel free to use that link. I'll go ahead and copy that to the other chats. Okay, we validate it. We're going to save it. And then we're going to generate bitstream. We should be good to go. Going back here in Vitis, we have a platform. We're going to go ahead and build the platform, and then we're going to build the application. I need to bring up the. Bring up the new. Okay, let's bring up the start guide. I think it's this. Okay. Yeah, that's what going. I'll bring that over later. I'm actually going to modify the platform. I'll let it build first. We have everything running. So on the Vivado side, our block diagram is doing out of context synthesis on all our IP blocks. And then it's going to do a top level synthesis and then go through the place and route stages. In the platform BSP, I want to go modify the application processor standard out and standard in. This is very useful when UART can be connected to some other interface. In this situation, we're going to do JTAG only for our first processor. So we're going to change these to the PSU core site. And core site will just report its output down here in the bottom. So it's great if you just want to do JTAG and the output just immediately goes to the Vitis software. We are going to have to rebuild the platform just because this is defining the standard in and standard out for your processor. So this is where you would change that. If you have multiple UARTs, if you want to use core site, with 6 different processors, you may want them to be on different core sites or different UARTs, so this can be useful. So I want to focus. Hard to tell. I may set up the Razer camera so we can see it on this view. Okay, do this real time. So for this board, right, we have the MP sock board here. Here's the back side. Here's the front side of the processor. Light up a little bit. Didn't diffuse well. Focused a little bit well there. There we go. To run this in JTAG mode, we're going to change the boot pins. The boot pins are a small little switch. See, right there. Angle it. Those are the boot pins, the dip switches for the boot pins. That's going to change between JTAG, eMMC, and QSPI. We're going to set the JTAG mode, and that's in the documentation. Bring that up. So in the documentation, right here, we basically want to do off for both dip switches to go into JTAG mode. And now in our example projects over here, we're going to generate a Drystone application for the application processor. And just go through all the default settings and let it build. And let me get the JTAG. Board. Too many USBs. Okay, the board is powered. Let's go ahead and build. I like only building the application, but I'll save this as a workspace definition. So now we're going to run the system. So we go to, this is going to run the first stage bootloader. Then it's going to run the application. And it's going to report over the core site interface. So we're not doing using any UART right now. We're just using JTAG. So we had the first stage. Okay, we'll let the debug come out, and then we can talk about what we saw in the XSDB console. This will report once the benchmark reports ends, it reports. So this is the default settings. You can definitely optimize this within the processor. You can get up to like 3.0 for the application processors. But we had the first stage bootloader right here was loaded to Cortex, was loaded to the same processor, I believe. Once that ran, we then loaded the application to the A53 number 0, and then we executed it. So now we want to look at using, there's a Raspberry Pi 240 on this board that does a Xilinx virtual cable. So what we're going to do now is we're going to run the Drystone on one of the real-time processors, but we're going to use the Raspberry Pi JTAG forwarding. So let's go ahead and get the Drystone application set up for that. So we're going to do Drystone R0 for the real-time processor. And then when we go here, we're going to hit create new, give it a few seconds to populate the fields. And then we can just do the R0 BSP and hit next. We're going to leave that default to the UART. And there's another GitHub which has this repository for their board. We're using this one right here. And over the bottom left, the bottom left JTAG right here, or bottom left USB-C, provides us JTAG and UART. And if you follow the directions in the README, go down to them. What you want to do, where does it, right here. So you want to use, I'll pull it up real quick. You want to use this little application, side dag. We're going to go to, oh, I don't have it hooked up. Let me hook it up real quick. Not right now. Okay. So we're going to go to there we go. So what we want to do is we want to go to vendor 1, interface 3, and we want to set that up with libusbk. So you can add that driver for the Raspberry Pi so you can interact with it. And then in the builds right here, they have a pre-built executable. They have the firmware where you can build this yourself, but if you want to just use their pre-built Windows executable, it's right here. And let's show that working. So what we're going to do is we're going to run the executable, sets up the buffer. Now what we're going to do is we're going to open up a Tickle shell and connect to the hardware server that is on the system. And we're going to connect Xilinx virtual cable URL, use the local IP and the port 2542. And this will communicate with this Pico program. We can do targets, and we see the system. Now let's try to get this running. We need to rebuild the platform, and then build the application for the real-time processor. Brian asked what configuration. I used the default configuration for the MicroBlaze 5 or for the RISC-V implementation. You say we have a different implementation or explanation. Yeah, I'm just using the default. I haven't modified the RISC-V implementation at all. And we can go ahead and show this link here that Sundance has. Sundance has a MicroBlaze-V explanation. I'm not curious if they offer like the best configuration, but there's different things you could add. It's a soft processor. You can add and disable different features, reliability features, different utilities. But the MicroBlaze-V processor is accessible on all FPGAs. So it allows you to go from something that has a hard processor to something that's purely fabric. So going to our real-time application, we're going to build this. Hopefully this works. We may have to, did it show up on this? Okay, it's happy at least. So we're using the UART for this, so we'll go ahead and run it, make sure it finds what it's looking for. It looks like it did. Bring over the UART. Okay, that's the first stage bootloader. Once it finishes loading, we see the first stage bootloader in the UART. Let's go ahead. This is just the first stage bootloader exiting. So it's just showing us the exit in the first stage bootloader. And there's the application running. We can go into the terminal. We can increase the font. 14, I guess. Okay. first stage bootloader, and running a system. So this is using the Xilinx virtual cable over the Raspberry Pi 240. And let me head back to our chats, make sure we have anything else. Okay, going back to our Vivado project, our bitstream is finished. And we can look at the reports for that after we get the system up and running. But we're going to export the XSA again, but this time we're going to include the bitstream for the system. And we'll give it a different name so we can tell what's happening. If you're joining us, it has been like about 30 minutes, 30 more plus minutes into the stream. This is a stream. We are looking at the VCS3 3D kit with the AMD MPSoC FPGA SoC with ARM processors. We're going through a Vivado project right now to show you how you enable the processors and do basic software loads on it. And Sundance is offering a voucher, so feel free to email them to get the appropriate code to get a 50% discount on the products that we talk about today. We have just built the application for the ARM processor, application A53, and the real-time processors, the R5 processors. Now we are looking at the MicroBlaze, which is going to be a soft processor implemented on the system. So in Vitus, we're going to go ahead and do a new platform specifically for the MicroBlaze, which includes the bit file. And we have the top hardware. And if there are any other questions, feel free to ask. Brian Fletcher has another comment in LinkedIn, which is useful. He says the default configuration of the RISC-V or MicroBlaze RISC-V processor is a RV32 IMC, so it has the integer multiplication and compression extensions, and it's a great default for bare metal or Zephyr real-time operating system. We're not going to generate the boot artifacts for the MicroBlaze. We're going to be using the Tickle PSU init script. We'll let it build the platform, and then we'll do the Drystone benchmark on the MicroBlaze-V. While this is running, we can go ahead and open the implemented design so we can see how the FPGA is placed and routed, and look at the timing summary and the utilization summary of doing a basic MicroBlaze-V design. Okay, build this platform. So in this platform, the MicroBlaze is using a JTAG-based debug UART. It does not have, I did not give it access to the UART in the processor. I believe there's a way you can have it drive the registers there, but it's not a default configuration in Vitus or Vivado. It takes a bit of work. Usually you would use your own PL-based, fabric-based UART but there are ways to set up communication or a mailbox with the other processors and forward that data. But we're just going to use the JTAG for now. Okay, let that finish, and then we can run the MicroBlaze design. Okay. Oh, power summary. What power summary do we have here? 1.84 watts. Typical. The power, you really need to go in and specify your specific situation to get a really good power estimate in this situation. We look at the device. This is the one we want. We'll do this. Here's the ARM processor system, and here's where we have the MicroBlaze with the various peripherals. It looks like it's taking a good chunk, but if we look at the utilization report, it's probably a lot smaller than what you think it is. We go to summary. We are only using 3% of the fabric, or 4% if you round up, and 7-8% of the VRAMs. So it looks like, even though it looks like it's a good 6 of the design, we're actually using less than 1/10 of the FPGA. So keep that in mind. The timing report, yeah, we can make this processor probably go twice as fast. Running at 100 megahertz, we probably push it to 200 megahertz or faster on this design. Okay. We're going to build the MicroBlaze-V. I'm going to go into the launch JSON. We're going to use the tickle instead of the first stage bootloader. Vitus seems to have an issue with the first stage bootloader and a MicroBlaze-V heart on the same system. For some reason, the first stage bootloader by default is not very happy with that, so I have to go do the tickle initialization. But let's go ahead and try to run this. We should see the output in XSDB. I may have to, hopefully we don't have to restart it. Going between the virtual cable and the real JTAG and all these different interfaces can sometimes make the XSDB Vitus connection a little tricky. Okay, it's downloading, or it's configuring the FPGA, not downloading, it's configuring the FPGA over JTAG. We have a question from Paul in LinkedIn. Was the Xilinx virtual cable Raspberry Pi 240 to provide another JTAG UART interface? Yes. It replaces, when you when you power the Raspberry Pi 240, it replaces the JTAG interface, so you have to use the Xilinx virtual cable, but it provides you the UART as well. It'd be interesting if there's a configuration where you could disable the virtual cable and be able to use it just for multiple UART channels. And maybe that'd be interesting if you could support multiple UART channels, so you could have multiple UARTs to the different subsystems. But for now, yes, it replaces the JTAG and the UART. Okay, so we had the UART here. The MicroBlaze-V has a little issues with this, so let's go look at it in a better format. I'll show you how to set this up. So we go to targets, we go to target 17 right there, and we go to help streams. So target 17 is the RISC-V at user 2, which is a B-scan. We can start a JTAG terminal at target 17. So we just do JTAG terminal, and this is going to open up an additional window where we have dedicated communication. And then we can go to target, 18, we can do a reset, and now it's rerunning, and we can see the output of the MicroBlaze running here. The MicroBlaze-V is actually good enough that it runs better than the default expects it to, and doesn't actually do enough iterations of, actually no, it did on the default settings. That's our the DMIPS per megahertz. Let me show you how to change the the iteration. So we're gonna go here, and I think it was here where the iteration is defined. Was it not? Right here. We're going to increase the iteration by 10x, and then we're going to go to the user config cmake, go to optimization, and we're going to up it to 03. Now let's rebuild the MicroBlaze. So we're going to improve the compiler optimizations. We increase the runs so we can get like a good output. So we'll see how we jump from 0.4 and see what the new 0.48, see what the new solution is. Okay, it's not happy with the JTAG, so we're going to, I think we're seeing it here. So we're going to go, let me restart that real quick. Connect here. Try again. The Xilinx virtual cable doing the MicroBlaze. Since this, okay, we are programming it. Since the Xilinx virtual cable is being bit banged over the Raspberry Pi 240, and it's not a robust program, right? It probably needs some optimizations and improvements. There's some times you're gonna have to reset it when you're trying to communicate between Vitis, Xilinx virtual cable, and the tool. Okay, looks like we're making it. I may need to redefine. Okay, it's actually running here. Okay. Okay. Performance here, the MIPS was 1.4. So we went from, we gained almost a 1x. We didn't see here because we have to go through targets. It's now target 15. We'll do a JTAG terminal and bring that over here. Go with target 16 and just do a reset. Now we can see the benchmark. Oh no, was it? Already has 1.48 there. Okay, so it already saw previous stuff. So that's a great improvement, right? 1.48, that's a great improvement with the optimizations. And we can see the same type of optimizations on the R5 and A53 processors with the appropriate compile optimizations. So, sorry we were kind of, that was a little fast. I was trying to hit from scratch how we can look at all the processors available on this system, how you can boot it up, run some software. You can easily load in your own software, be able to run through the different examples. But within an hour, basically from scratch, we can get something running on the system, a custom load running on the system, which is great. I always find it really helpful when you can get something up and going that fast. Here's some topics that I want to explore in this upcoming video campaign series. We want to look at the PL Fabric camera pipeline. There's a lot of IP that Vivado provides that allows you to take that raw video data and bring it into the processor system or just operate it on the fabric by itself. There's also a display pipeline, which allows us to overlay and pick different interfaces and stuff like that, which is really grateful if we want to do some type of detection and monitor detection. Maybe like following a colored object or something like that. There's also processor video pipeline system. There's an display input, and display output built into the MPSoC hardened processor. A lot of people don't really explore it. It's mostly used for very basic examples. I would really love to explore in more detail to see if we can utilize that as another video channel within the system. Next topic, Linux EDF. This is the new Linux flow that AMD and Vivado, whatnot are using for their future products. I think it'd be great to explore maybe the old system and the new system and getting it working with Pink. And Pink is great because it allows you to upload bit streams or partial bit streams to be able to swap out functionality without bringing down the FPGA system. I think Pink is great for a system like this where it's kind of isolated. Get like a Wi-Fi USB or a dedicated USB data cable, and you can easily move on and off new bit streams, partial bit streams, be able to play around with different FPGA configurations. The last thing, since this is an isolated system, the best way to move data on and off the system is USB-C. That can be, with Linux, you can do a USB Wi-Fi. I'd be curious to try to get bare metal data flowing from this system to maybe like a Linux or a Windows system. So I'm going to be looking at the best way to move data. I definitely want to demonstrate different video stream like snapshots to you, and I can't, showing this display on camera is not going to be very effective. So I want to look at some USB-C data. So we're going to have a few more minutes for questions. I'm going to leave the voucher email up so you can copy it down and make sure if you want to get a 50% coupon on any of the products from Sundance that we talked about. But I am FPGA Zealot. You can find recordings on YouTube, Twitch, on LinkedIn. Feel free to jump onto Discord in the description and ask questions. I'll try to answer any questions in the chats. And we should have a Hackster IO article coming out tomorrow, the day after, with a good description of what we did here so you can follow along. And then we'll just go back to the voucher code. So yeah, this is the time. Please ask any questions, any feedback, any comments in LinkedIn, Twitch, or YouTube. Feel free to leave like a like, subscribe, whatnot, just to show, I guess, your interest in supporting future videos. And thank you. Okay. Hard to tell where state everything is in. Martin, thank you for the great feedback. I know it's a little rapid fire, but there is a lot to go over in a short amount of time. But hopefully an additional Hackster article and whatnot, this being a recording, you'll be able to follow along as we go through. Yeah, on Twitch, you can watch the VOD on Twitch, YouTube, or LinkedIn. I'm not sure which one is the best quality. I haven't really tested them. I do have videos later this week and next week. We'll be looking at USB PCIe across 2 different FPGA families on Friday, my Friday, in the afternoon. On Tuesday next week, we'll be looking at a RISC-V processor on a kind of a space grade FPGA, which will be interesting. A soft RISC-V processor. And then we'll probably do a Quartus DDR configuration video and then we'll return back to the Sundance 3D kit in probably about 2 weeks. Paul, you asked a great question on LinkedIn. So I'm using the AMD tools in Windows. Mostly that's just kind of my default system, but I do have a few Linux machines, and the AMD tools work just as well, are better on Linux. I do want to set up a Docker image for this project, so that's probably what I'll be working on this weekend, is try to publish a Docker image that supports all the tools and files that you need to get to repeat everything I do. A Docker image is not terribly critical for like Vivado and Vitis, but for Linux, generating a stable Linux, a deployable Linux system for the board, a Docker image can be very useful. So I think while these AMD tools don't necessarily need a Docker image or a VM, when we get to the Linux portion of this, we definitely want to start from a stable Docker image or VM. Another comment on YouTube. Great stream. Looking forward to the Petalinux session. Me too. I need to go set all that up. The default Petalinux isn't really that hard. I'm a little worried about the new EDF system just because I haven't done it before. Also, I'm not sure how well Pink is compatible with Linux EDF. I assume it should work fine, but I'm not sure what differences will be from Petalinux. Okay. Okay, I'll give everyone probably about 3 more minutes to post the question. I'm not sure what the delay is with the different services, but hopefully in the next 3 minutes we can see any final questions or comments and be able to address them. So thank you for joining us. Thank you, Sundance, for providing the hardware. Thank you for the voucher coupon for the people watching it. I do think a 50% discount on the VC3 core is a great deal. I don't think you're going to be able to find an equivalent hardware that comes with good support from Sundance, provides you QSPI, eMMC, LPDDR4, in a small little package. So I do think the 50% discount on the VCS3 core is a great deal. The 3D kit, you can buy these boards separately and do your 3D kit yourself, which does allows you to pick different cameras, different mounting options, different display. So I do think that's a great option as well. So if you look at the core and the board, the core and the board in this Raspberry Pi board, and if you're a creative person, you can find different ways to mount this system. I'm wondering if you could do like a handheld 3D camera. That would be really cool. Turn this into like a handle, and then do like a 3D camera. I'm not sure what's the best way to do that, but like a handheld 3D camera would be really, really cool. Now I want to do that. So we have a question on Twitch, how we're getting the video data from the cameras to our host computer. So this system is pretty isolated. What they've done is they made this USB-C. There's a USB-C on this little thing. And when you plug that into Linux, you have a high-speed USB-C, you can do whatever you want. You can do Wi-Fi, you can do Ethernet, you can do direct to a system. So right now there's no obvious like HDMI or display port that you can hook up to a capture device or your computer or anything like that. You might be able to use a USB video output. I'm not sure what the Linux drivers in the MP-SOC will think of that, but you should be able to do that. I'm not sure what the quality will be, but you definitely could do USB Ethernet to 2.5 gig. 2.5 gig Ethernet, and be able to do like UDP streaming to your host computer. That might be like the best option. It'll probably be the first thing I'm going to explore. I need to find a USB 2.5 gig Ethernet now. But thank you for the question. Okay, so we're about to reach the hour of streaming. Thank you all for joining us. I look forward to seeing you again as we do more video processing on the system. We're probably going to start with examples in bare metal and move up to how they work in a Linux application. I'm much more of a bare metal person, get bare metal working first, then Linux. But I look forward to seeing you in future videos. And thank you for joining. I'm going to probably just turn them all off. I will see you in the next stream.